Imagine standing on the deck of a destroyer in 1945, watching your ship's new weapon system tear through the sky with deadly precision. Now imagine learning that this technology was invented by the very enemy you just defeated. This is the untold story of how America transformed captured German and Japanese naval weapons into the backbone of modern United States naval power. What you're about to discover will change everything you thought you knew about American military innovation. The Pacific Ocean stretched endlessly before the USS Missouri as it sailed into Tokyo Bay in September 1945. World War II was over, but for American naval intelligence officers, the real work was just beginning. Hidden in dockyards across Japan and Germany were technological marvels that would reshape naval warfare for generations to come. These weren't just weapons. They were glimpses into the future, and the United States Navy was about to claim them all. The story begins not in 1945, but years earlier, when German and Japanese engineers were pushing the boundaries of what naval weapons could achieve. While American factories churned out reliable, conventional weapons, Axis powers were experimenting with revolutionary concepts. Acoustic torpedoes that hunted ships by sound, guided missiles that could think for themselves, submarine technologies that made vessels nearly invisible beneath the waves. The Allied forces knew these weapons existed, but they had no idea just how advanced they truly were. When the first German U-boats were captured intact in the Atlantic, American engineers couldn't believe their eyes. The Type 21 submarine represented a quantum leap in underwater warfare. Its streamlined hull could slice through water at unprecedented speeds. Its schnorkel breathing system allowed it to remain submerged for weeks. Its battery capacity dwarfed anything in the American fleet. This wasn't just an incremental improvement. This was a complete reimagining of what a submarine could be. The capture of U-2511 in May 1945 gave American naval intelligence its first complete look at German acoustic torpedo technology. The Zonkenig torpedo, which the Germans called the Gnat, could actually listen for the sound of a ship's propellers and steer itself toward the target. American submariners had been manually aiming torpedoes throughout the entire war, often missing their targets despite perfect positioning. Now they held in their hands a weapon that could do the thinking for them. But the real treasure trove wasn't in the Atlantic. It was waiting in Japan. When American forces occupied Japanese naval facilities in 1945, they discovered weapons programs that seemed lifted from science fiction. The Japanese had been working on guided missiles, human-guided bombs, and kamikaze submarines. They had developed oxygen-fueled torpedoes that left no telltale bubble trail. They had created shipborne rockets that could shoot down aircraft with devastating accuracy. And they had done all of this while fighting a losing war on multiple fronts. Operation Paperclip is famous for bringing German rocket scientists to America, but few people know about its naval counterpart. The Navy's technical intelligence teams fanned out across occupied territories with a simple mission: find everything, document everything, and bring it all home. They weren't just looking for weapons. They were looking for blueprints, test data, prototypes, and most importantly, the engineers who designed them. What they found exceeded their wildest expectations. The German Type 21 submarine became the template for America's post-war submarine fleet. Navy engineers spent months studying every inch of the captured vessels, measuring hull dimensions, testing equipment, and interviewing captured German submariners. The streamlined hull design that allowed the Type 21 to reach 17 knots submerged would influence American submarine design for decades. The Guppy conversion program, which modernized American fleet submarines after the war, borrowed heavily from German innovations. Japanese torpedo technology was equally revolutionary. The Type 93 torpedo, known to the Allies as the Long Lance, was the most advanced naval torpedo in the world. Powered by pure oxygen instead of compressed air, it could travel 20 miles at 48 knots without leaving a visible wake. American torpedoes at the start of the war could barely manage 9 miles at 45 knots, and they left a trail of bubbles that warned targets of their approach. When American engineers finally examined captured Long Lance torpedoes, they realized the Japanese had been fighting with a weapon years ahead of anything in the Allied arsenal. The acoustic homing technology from German torpedoes transformed American submarine warfare almost overnight. By 1947, the United States Navy had developed its own acoustic torpedo based on captured German designs. The Mark 24 mine, actually an airdropped acoustic homing torpedo, entered service and immediately proved its worth against enemy submarines. This wasn't just copying. American engineers took the German concept and refined it, creating weapons that were more reliable and more deadly than their predecessors. German surface-to-air missile technology opened entirely new possibilities for naval defense. The Wasserfall missile, designed to shoot down high-altitude bombers, never saw combat during World War II. But American engineers recognized its potential immediately. A ship equipped with guided missiles could defend itself against aircraft at ranges previously impossible. The Navy's Bumblebee project, launched in 1945, drew directly on captured German missile technology. Within a decade, American destroyers and cruisers would bristle with guided missiles that could swat aircraft from the sky. The schnorkel, that simple breathing tube that allowed submarines to run diesel engines while submerged, revolutionized submarine operations. Before the schnorkel, submarines had to surface regularly to recharge batteries, making them vulnerable to aircraft attack. German Type 21 submarines could remain submerged for weeks using their schnorkels. American submarine crews who had spent the war surfacing every few days to recharge batteries immediately grasped the tactical advantage. By 1947, the Navy was retrofitting schnorkels onto its entire submarine fleet. Japanese radar and radio technology surprised American intelligence officers. Despite being portrayed as technologically inferior throughout the war, Japanese engineers had developed sophisticated radar systems and radio-controlled weapons. The Funryu surface-to-air missile system used radio guidance to intercept aircraft. The I-400 class submarines carried seaplanes that could be launched for reconnaissance or attack missions. These weren't primitive weapons. They were sophisticated systems that rivaled anything the United States had developed. The human cost of this technology transfer is often forgotten. Many of the German and Japanese engineers who designed these weapons were recruited to work for the United States. Some came willingly, eager to continue their research. Others came reluctantly, prisoners who saw cooperation as their only option. They lived in guarded facilities, working alongside American engineers who had spent years trying to kill them. The tension was palpable, but the work continued. National security demanded it. The captured German wind tunnel data proved invaluable for developing supersonic missiles and aircraft. German engineers had conducted thousands of hours of wind tunnel testing on advanced aerodynamic shapes. This data, meticulously recorded in notebooks seized from German research facilities, saved American engineers years of research. The sleek, swept-wing designs that would characterize Cold War American fighters and missiles owed much to German research conducted in the final desperate years of World War II. Japanese submarine designs influenced American thinking about underwater warfare in unexpected ways. The I-400 class submarines were the largest built during World War II, true underwater aircraft carriers capable of circling the globe. While American admirals initially dismissed them as impractical, the concept of submarines as strategic weapons platforms took root. The modern ballistic missile submarine, capable of remaining hidden beneath the waves while threatening entire continents, traces its conceptual lineage directly to those massive Japanese submarines. The magnetic influence mine technology captured from Germany changed naval mine warfare forever. These sophisticated weapons could detect the magnetic signature of a ship's steel hull and detonate without physical contact. American minesweeping technology had barely kept pace with conventional contact mines throughout the war. Suddenly, the Navy faced an entirely new class of mine that required new detection methods and new countermeasures. Captured German mines provided the blueprint for developing both better mines and better ways to find them. Rocket-assisted projectiles captured from Japanese naval facilities pointed toward the future of naval artillery. The Japanese had experimented with adding small rockets to artillery shells, extending their range beyond what conventional propellants could achieve. American ordnance engineers immediately recognized the potential. By the 1950s, rocket-assisted projectiles would extend the range of American naval guns by 30% or more, giving cruisers and battleships the ability to strike targets previously beyond their reach. The captured German Walter turbine submarine propulsion system represented a dead end, but a fascinating one. Helmuth Walter had developed a submarine propulsion system using high-test hydrogen peroxide that could achieve underwater speeds of 25 knots. The system was dangerous, temperamental, and ultimately impractical. But studying it taught American engineers valuable lessons about high-speed underwater propulsion that would inform nuclear submarine design a decade later. Japanese optical range-finding technology was among the finest in the world. The long-base rangefinders mounted on Japanese battleships could accurately measure distances out to 20 miles. American ships used similar technology, but Japanese optical quality was superior. Captured Japanese rangefinders ended up in American laboratories, where engineers studied their lens grinding techniques and optical coatings. This knowledge flowed into American optical manufacturing, improving everything from binoculars to periscopes. The influence of captured enemy technology extended beyond hardware. German tactical doctrines for submarine warfare influenced American submarine training for years after the war. The German concept of wolf pack tactics, where multiple submarines coordinated attacks on convoys, had devastated Allied shipping in the Atlantic. American submarine commanders studied German tactics, learning what worked and what didn't. This knowledge shaped American submarine doctrine throughout the Cold War. Japanese naval aviation tactics also left their mark. While the kamikaze attacks of 1944 and 45 were desperate measures born of desperation, they revealed vulnerabilities in American naval air defense. The Navy invested heavily in developing better radar systems, better anti-aircraft guns, and better fighter direction procedures. Many of these improvements drew directly on lessons learned from defending against kamikaze attacks. The Combat Information Center, nerve center of modern warships, evolved in direct response to the kamikaze threat. The captured German infrared night vision technology opened new possibilities for nighttime naval operations. German tanks and ships had been equipped with primitive infrared searchlights and viewers that allowed them to see in darkness. American engineers improved on these designs, developing night vision systems that gave American ships and submarines a crucial advantage in low-light conditions. By the 1950s, American warships could fight effectively in complete darkness using captured and improved German technology. Remote-controlled boats and missiles developed by both Germany and Japan pointed toward the future of unmanned warfare. The Germans had experimented with explosive-laden remote-controlled boats designed to attack Allied ships. The Japanese had developed similar systems. While these weapons saw limited combat use, they represented early attempts at what would eventually become unmanned aerial vehicles and autonomous weapons systems. American engineers studied these early drones carefully, filing away lessons for future development. The technical intelligence gathering process itself became a model for future operations. Navy teams developed standardized procedures for documenting captured technology, interviewing enemy engineers, and shipping equipment back to the United States. These procedures, refined during the occupation of Germany and Japan, would be used again in Korea, Vietnam, and countless smaller conflicts. The institutional knowledge of how to exploit captured enemy technology became a permanent part of American military intelligence. Testing captured weapons revealed uncomfortable truths about American technological complacency. In many areas, German and Japanese weapons were simply better than their American counterparts. American torpedoes at the start of World War II were notoriously unreliable, often failing to explode or running too deep. Japanese torpedoes, by contrast, were devastatingly effective. This gap in performance forced the Navy to confront systemic problems in its weapons development and testing procedures. The integration of captured technology into American weapons systems happened remarkably quickly. By 1948, just 3 years after the war ended, American submarines were using acoustic torpedoes based on German designs. American destroyers were testing guided missiles derived from German rockets. American aircraft carriers were employing fighter direction techniques learned from defending against kamikazes. The peacetime Navy of the late 1940s looked very different from the wartime Navy of 1945, and much of that difference came directly from captured enemy technology. Security concerns surrounded the technology transfer program from the beginning. American intelligence agencies worried that Soviet forces occupying eastern Germany and northern Korea would capture similar technology. The race was on to grab everything of value before it fell into Soviet hands. In some cases, American teams destroyed equipment they couldn't transport rather than risk Soviet capture. In others, they removed key components and destroyed facilities to prevent Soviet exploitation. The ethical dimensions of employing former enemy engineers troubled some Americans. These were men who had designed weapons to kill American servicemen. Now they were working in American facilities, drawing American paychecks, and contributing to American military power. The Navy's position was pragmatic. The technology existed. Either America would exploit it or someone else would. Better to have these engineers working for the United States than against it. Not everyone agreed with this logic, but national security concerns overrode moral objections. Soviet exploitation of captured German and Japanese technology created a technological arms race that would define the Cold War. The Soviets captured as much or more enemy technology as the Americans, along with hundreds of German and Japanese engineers. Soviet submarines incorporated German design features. Soviet missiles used German research. The technological competition between America and the Soviet Union in the 1950s and 60s was, in many ways, a competition to see who could best exploit captured World War II technology. The long-term impact of captured enemy naval technology on American military power is difficult to overstate. Modern American submarines trace their lineage through continuous evolution back to those captured Type 21 U-boats. Guided missiles, now the primary armament of American surface warships, descend directly from German surface-to-air missiles and Japanese anti-ship weapons. Even modern naval tactics reflect lessons learned from studying enemy operations during World War II. Training programs evolved to incorporate captured technology and tactics. The Navy established schools specifically to teach officers how to use new weapons systems derived from enemy technology. Submarine school curricula expanded to cover schnorkel operations and acoustic torpedo employment. Surface warfare schools added guided missile tactics. The institutional knowledge base of the United States Navy grew exponentially in the years immediately following World War II, fed by a flood of captured enemy information. Industrial partnerships between the Navy and private contractors accelerated technology transfer. Companies like General Electric, Westinghouse, and Raytheon received contracts to study captured enemy equipment and develop American versions. These companies hired German and Japanese engineers to consult on projects. The result was a seamless flow of technology from enemy hands to American production lines. Within a few years, American factories were producing weapons that had been enemy exclusives just a short time before. The captured enemy technology also influenced American naval architecture. Destroyer designs in the 1950s incorporated lessons learned from German and Japanese warships. The placement of weapon systems, the arrangement of radar antennas, even the internal layout of ships reflected analysis of captured enemy vessels. American naval architects studied what worked well in enemy designs and what didn't, incorporating the best features into American ships. Sonar technology benefited tremendously from captured enemy research. German engineers had been working on passive sonar systems that could detect enemy submarines without giving away their own position. Japanese engineers had developed advanced underwater sound propagation models. American sonar research, already strong, leaped forward by incorporating these captured insights. The sophisticated sonar suites that made American Cold War submarines so effective owed much to German and Japanese research. Anti-submarine warfare doctrine transformed, based on lessons learned from fighting German U-boats. The combination of aircraft, surface ships, and submarines working together to hunt enemy submarines became standard American practice. The barrier tactics used to close off strategic waterways, the hunter-killer groups that tracked down individual submarines, even the coordinated attacks using multiple weapons platforms all reflected hard-won lessons from the Battle of the Atlantic. The psychological impact on American naval officers and engineers shouldn't be underestimated. Many had spent the war believing in unquestioned American technological superiority. Discovering that the enemy had been ahead in numerous areas was humbling. It fostered a culture of continuous improvement and healthy respect for potential adversaries that served the Navy well during the Cold War. Complacency, once shattered, was difficult to rebuild. Maintenance and logistics systems evolved to support the new technologies. Acoustic torpedoes required different handling procedures than conventional torpedoes. Guided missiles needed specialized maintenance facilities. Submarines with schnorkels needed new training protocols. The Navy's entire support infrastructure had to adapt to accommodate weapons and systems that hadn't existed a few years before. This adaptation happened remarkably smoothly, testament to the Navy's organizational flexibility. The documentation captured alongside physical equipment proved as valuable as the hardware itself. German and Japanese engineers had produced thousands of technical manuals, test reports, and design studies. These documents provided blueprints for American engineers trying to reverse engineer captured systems. In some cases, The documents revealed abandoned research projects that American engineers could revive and complete. The paper trail of enemy research became a roadmap for American weapons development. Budget battles in Congress often cited captured enemy technology as justification for new weapons programs. When the Navy requested funding for guided missile cruisers in the late 1940s, admirals pointed to captured German missiles as proof of concept. When submarine modernization programs needed approval, senators received demonstrations of schnorkel-equipped submarines. The captured technology provided concrete evidence that revolutionary new capabilities were possible, making it easier to secure funding. International cooperation complicated technology exploitation. Britain, Canada, and other allies had also captured enemy equipment and wanted access to American findings. The Navy had to balance security concerns with alliance obligations. Some technology was shared freely. Other developments remained closely guarded American secrets. These decisions created tensions that occasionally strained Allied relationships, but they also fostered continued cooperation in naval technology development. The transition from wartime to peacetime development happened against the backdrop of captured technology exploitation. Engineers who had spent the war designing weapons to defeat Germany and Japan now found themselves studying and copying German and Japanese designs. The irony wasn't lost on anyone involved, but the work was too important to let sentiment interfere. The Soviet threat was emerging, and America needed every technological advantage it could obtain. Testing facilities expanded dramatically to accommodate captured equipment. Wind tunnels grew larger to test captured German missile designs. Submarine test facilities modified their equipment to handle new propulsion systems. Torpedo ranges installed new instrumentation to measure acoustic weapon performance. The physical infrastructure of American naval research and development grew to match the expanded scope of work created by captured technology. Civilian applications emerged from military technology transfer. Improved optical coatings developed from studying Japanese rangefinders found their way into cameras and eyeglasses. Sonar technology spawned commercial fish-finding equipment. Even schnorkel technology influenced civilian submarine designs. The military technology captured from enemies rippled outward, touching civilian life in countless subtle ways. The competition between the Army, Navy, and Air Force for captured technology created bureaucratic battles. All three services wanted access to enemy research, and all three claimed jurisdiction over certain technologies. The newly independent Air Force particularly clashed with the Navy over guided missile development. These inter-service rivalries, while frustrating, ultimately pushed each service to innovate more aggressively, accelerating overall American military technological advancement. Looking back from the 21st century, the scale and speed of the post-World War II technology transfer seem almost unbelievable. In just a few years, the United States Navy absorbed and integrated revolutionary technologies from defeated enemies, transforming itself from a conventional fleet into the world's first truly modern navy. Acoustic torpedoes, guided missiles, advanced submarines, sophisticated radar systems, all became standard American equipment in less than a decade. The human stories behind the technology transfer are equally remarkable. German engineers who had designed U-boats to sink American ships found themselves teaching American submariners. Japanese torpedo designers who had created the long lance worked alongside American ordnance experts. Former enemies became colleagues, united by shared professional interests and the demands of the Cold War. These personal transformations mirrored the larger strategic realignment that made yesterday's enemies into today's partners against a common Soviet threat. The legacy of captured enemy technology extends to the present day. Modern American naval weapons still bear the genetic markers of their World War II ancestors. The Tomahawk cruise missile is a direct descendant of German V weapons and Japanese guided bombs. The Virginia-class submarine incorporates design lessons learned from Type 21 U-boats 80 years ago. The Aegis combat system traces its conceptual roots to the fighter direction centers developed to counter kamikaze attacks. Perhaps most importantly, the experience of capturing and exploiting enemy technology taught the United States Navy institutional lessons that remain relevant today. The importance of technical intelligence, the value of learning from adversaries, the necessity of remaining humble about technological advantages, the need for continuous innovation. These lessons, learned in the occupation zones of Germany and Japan, continue to shape American naval thinking in an era of competition with China and other near-peer adversaries. The story of captured German and Japanese naval technology isn't just history. It's a reminder that military advantage is fleeting, that yesterday's innovations become today's standards, and that the willingness to learn from enemies can be as important as the ability to defeat them. The American sailors and engineers who recognized the value of captured enemy technology and worked to integrate it into the United States Navy built a legacy that continues to protect American interests around the world. As we stand on the decks of modern American warships, surrounded by sophisticated weapons systems and advanced technologies, we should remember that many of these capabilities trace directly back to enemy innovations captured 8 decades ago. The submarine gliding silently beneath the waves uses propulsion concepts first proven in Type 21 U-boats. The guided missiles in their launchers descend from German Wasserfall and Japanese Funryu weapons. Even the radar systems scanning the horizon reflect lessons learned from Japanese fire control technology. We stand on the shoulders of former enemies who built well, even if they built for the wrong cause. The transformation of enemy weapons into American innovations represents one of the most successful technology transfer programs in history. It happened quickly, efficiently, and with lasting impact. It required vision to recognize the value of captured technology, humility to acknowledge that enemies had sometimes achieved superior results, and determination to integrate foreign innovations into American systems. These qualities served the United States Navy well in the transition from World War II to the Cold War. They remain essential qualities today, as America faces new technological challenges from new adversaries who are themselves racing to match and exceed American capabilities. The final irony is that the cycle continues. Just as America learned from captured German and Japanese technology, potential adversaries today study American weapons and tactics, looking for insights and advantages. The process of military innovation through technology transfer, espionage, and reverse engineering that served America so well in the 1940s now works in multiple directions. The question facing the United States Navy today is the same question that faced it in 1945. Can we innovate faster than our adversaries can copy? Can we maintain technological superiority in an era of rapid information flow and globalized technology? The answers will shape naval warfare for generations to come, just as the decisions made by those engineers studying captured enemy weapons 80 years ago shaped the Navy we have today.